Okay. So Henning, what do you think the relative mix of like CS and math people is in this call?
I don't know. I think it's I would guess 85% math people and like 15% like computer science, I would guess.
Okay.
I'm not sure.
Okay.
So I think most of we have a mailing list, and I think most of our like subscribers to the mailing list came from advertising on like SciM webs, like the SciM, like so applied math thing.
Gotcha. Gotcha.
Okay, I think, should we start?
Sounds good to me.
Okay, yeah. Welcome everyone to episode number 4 of the data-driven, like on a seminar series for data-driven methods for science and engineering. My name is Henning Lange. I'm one of the organizers alongside Jason Bramberger, Joe Bakker-G, and Jordan Snyder. It is my pleasure to introduce today's speaker, which is David Duvenaud. David Duvenaud is an assistant professor in computer science at the University of Toronto. His research focuses on continuous times models, latent variable models, and deep learning. His postdoc was done at Harvard and his PhD at the University of Cambridge. David also co-founded Invenia, which is an energy forecasting and trading company. And yeah, without further ado, the Zoom call is yours.
Thank you very much, Henning. Yeah, so it's a real pleasure to be here. And it's also a real pleasure to get feedback from mathematicians and people who I think have been thinking about differential equations for longer than I have. But to start off, I just want to say, I realize that I'm coming from a little bit of a different background than I think many of the watchers here. And I want people to feel free to speak up and say, I don't know what you mean. I'm pretty sure that when I talk, for instance, about backpropagation, that's at least a special case of what's typically called the adjoint sensitivity method. Or, you know, other people might talk about identification, and I'd say like fitting a model. Or I have this idea that joint approximate inference is when we make all the latent variables agree with the observations, but I think that's called things like backfitting in other fields. So please help me explain things clearly and interrupt with questions. And I think Henning, or one of the organizers, is going to be emceeing the chat, which I can't see the chat, but please interrupt me. Okay, so just to make it clear what I'm going to talk about today, so you can leave now if you find this, is that in the last year or two, me and some collaborators have developed a couple of new algorithms that fill in the missing pieces for fitting large stochastic differential equation models with arbitrary likelihoods and dynamics. And I guess I would say these are, I think, the promising new tool, or at least the promising old tool that we can now apply to all sorts of time series problems. So in particular, I'm going to say, yeah, based on stochastic differential equations with any parametric dynamics, which we, so for shorthand, you say neural network instead of parametric, or interesting likelihoods where the observations might have like, there might be like doctor's notes or temperature readings or who knows what, as long as we can write down, a probability of the data given the latent state in a differentiable way, we can train these models on any types of data in principle. And I'm going to claim that these have some advantages over the standard sort of pile of goo neural network where you just feed in the observations and make predictions, in that these are more like real physical models where there's a latent state that we might be uncertain about that's distinct from just like the hidden units of a neural network. And I guess one of the main reasons that I started getting into all this is because this automatically lets us handle missing observations. So a lot of this talk is going to be about how to build continuous time models, but there's going to be two new sort of technical contributions, which is one is how do we generalize the adjoint sensitivity method to stochastic differential equations? And astoundingly, this actually wasn't worked out until a year ago. And there's like these sort of last two parts that we will talk about, let us have this constant memory cost training algorithm and lets us use like black box adaptive higher order SDE solvers. Although of course, people who have actually used SDE solvers realize that like high order in SDE land means like 1.5 or something kind of weak like that. Okay, so the whole reason that I started getting into any of this was irregularly timed data sets. And it's kind of, I think, like a very embarrassing fact about machine learning today, that pretty much most of the methods that are being developed don't work on most of the real data sets that people have. So certainly we have great time series algorithms for things like video or sound or texts. And there's a lot of such data, but in terms of institutions with problems, like every hospital or business, for instance, has data on their patients or customers that looks something more like this, where this is actual real data from a patient in an intensive care unit over 48 hours. And all sorts of doctors and nurses are coming by and measuring his like temperature or his blood pressure or whatever. And this is just showing like, what are the different times or the different measurements, not even their values. And the point is that there's not really many models around that can sort of natively handle this data and meet the data where it lives. So people end up doing, I think, kind of crummy things like binning the data into hours and then averaging within an hour. And I think, someday we'll have a statistician's Hippocratic oath that says like, thou shalt not like mess with the data before we've actually shown it to our model. Yeah, so I mean, and we do have things like Gaussian processes or continuous time Kalman filters that can handle this. And I guess I would say we don't really know how to stick a lot of parameters in those models, is their main problem. So if we think there's some really complicated model of human physiology that we want to learn all of its parameters, it's not really clear how to tie that to a Gaussian process model or a Kalman filter, even though they can actually handle this data. But if we want to fit a huge recurrent neural network or something, it's not really clear how to address this. The closest model that I'll get to is these deep Markov models or deep Kalman filters, where you stick neural networks in the transitions. That's sort of where we're heading. Okay. Any questions about this so far? Okay. And I realized that, again, many of you have been studying ODEs longer than I have, or even longer than I've been alive. So let's just say, to refresh people and get our notation on the same page, I'm just going to introduce my notation and say that, in an ODE, we have some vector value of state z, changes continuously through time. That time change is given by some function f, which could be a parametric function, like a neural network. And we're going to, use these typically to solve initial value problems where we know the state at some initial time. We want to follow this gradient field defined by f to learn, to compute its trajectory. And of course, one sort of interesting conceptual point is that you can actually solve these with something really simple, like with Euler's method, where we just take a current state, move in the direction of the gradient field over and over again. In practice, that's a terrible method because we have a low order of convergence and we accumulate error without controlling it. So if we can keep everything in the continuous time setting, if we can avoid discretizing, then we can hand off all of our problems to continuous time adaptive solvers that will use, the last 100 years of numerics to use sophisticated extrapolation and the error control methods to do a much more efficient job of solving these differential equations. So right off the gate, I'm going to say, let's not just discretize with Euler at the first step, because if we do that, we can't recover, or we can't use continuous time solvers. Okay. So the biggest lesson of machine learning is you always want to start with the simplest possible thing that can work. So there is like a really nice, simple way we could build a native continuous time models with many parameters. And that's to take a standard. So first of all, a recurrent neural network can handle this data. So if recurrent neural network says, okay, there's some vector valued hidden state that's going to stay the same in between observations. And when I see a new observation, I'm going to combine this new observation with my old hidden state by some parametric function. Okay. Very simple. It's pretty much the simplest possible recipe that could work. We can also tell it how much time passed as well, if we want to let it, be aware of the delay. And then you might say, well, the main problem with this is that if I want to make a prediction at some intermediate state, I'm just going to always make the same prediction no matter how far ahead forward in time that I waited. So like a simple fix, I don't think this is a great model, but it fits everything we've been asking for so far, is to say, oh, okay, well, what if the hidden state evolves according to some ODE in between the observations? And I think this makes sense if you think of the hidden state as a belief state. And, you know, imagine, like, I think belief states should change continuously through time, even when we don't get new data. So for instance, let's say I agree to meet my friend at the bus stop at 1 o'clock, and then I get there and I don't see him. And as I wait, my relative belief about like when he's going to show up, what's going on with him is going to change continuously, even though I'm not getting any new data. And then when he does show up, aha, now I have learned something all at once. Okay. So this is just sort of here as a baseline to say, well, so far I've just said I want to handle this data, not anything else. These are methods that would handle it in principle. Okay, any questions so far?
We have one question. So what is the overall goal? Is it prediction or is it building a model from data?
Yeah, that's a great question. So I guess I would say it's prediction. And the beautiful thing about building a model from data is that it lets us answer many more queries about the future or the past or which data was important. It just lets us answer pretty much any query we can think of. So to say, I just want to do prediction, it's like, well, if you have a very prescribed notion of what you want to know based on what you have, sometimes it's overkill to build a big model. I guess I would say that for cases like for dealing with patients or businesses or whatever, usually there's a wide variety of different questions we want to ask the model. And we don't want to have to train a separate network for each of those queries. Yeah. Anyway, but I definitely think that there are situations where things are just simple enough and prescribed enough that these baselines will work well. So we should always start with those. Okay. So, and this is kind of a larger issue that I don't really have time to get into today, but RNN-based models are kind of weird because they're not latent variable models in the normal sense. So what I mean is that specifically this hidden state H, we don't think it's actually the state of the system. What it is it's like the state of the RNN as it observes the system. And so it encodes the information that we know about the state and our uncertainty, and all of this just kind of in a big mess that's hard to disentangle. It's also not a well-defined generative model. So if I ask, you know, okay, when will I expect to see the next observation? It's not really clear that this model can answer that natively. The other thing I guess I'll say is that it sort of has to learn how to combine information. And we already know how to combine information optimally if we have a true model, which is to use Bayes' rule. So this has a major pro, which is that if you learn everything from scratch, you don't have to worry about having a well-specified model. You can still make well-calibrated predictions. But I think we're also being data inefficient by asking our model how to, to learn how to combine information on its own. And it's going to not be able to generalize to new types of data as well. Okay, anyway, the key takeaway here is that I think there's some things that just throwing everything into a neural network can't do. Okay, so what would be a good example of a latent variable model that I do like? Yeah, so my favorite one, which is this deep Kalman filter or deep Markov model by Krishnan and David Sontag and others. And it's basically an extension of Kalman filters that says, okay, there's a true state of my system. It's like the position of my missile or the position velocity of the missile that I'm tracking, right? Because these were used in missile trackers for many decades. Transition function is just saying, okay, given the current state, what's my next state? And there's some stochasticity here. And the emission is basically saying, what does my radar cross-section look like, depending on where the missile is and how it's traveling. And if everything is linear-Gaussian, we can do inference exactly and estimate the position of the missile and our uncertainty in one step. If we want to put 6 more parameters in here, we suddenly have this really hard approximate inference problem of trying to estimate probability of Z or the whole trajectory of Z given the data. And we have to integrate out over Z if we want to train all these parts of our model by maximum likelihood. So this is like obviously a whole area of approximate inference and training. And I'm today I'm just going to talk about variational autoencoders as one solution where to integrate out the latent variables, we train another auxiliary neural network, which we call a recognition network, to give us an approximation to the posterior distribution over these Zs. And we can, that's just kind of an optional thing to speed things up though. The point is, variational inference is like a really nice tool that was only really, or stochastic variational inference is really only made mature in the last like 5 or 6 years. But now we do think that we can train huge latent variable models and actually approximately integrate out these latents, even when things are nonlinear and non-Gaussian. Okay, any questions so far?
There is one question, which is, are continuous time solvers truly continuous? Is there no discretization in time?
Well, that's fair. I guess I would say we don't want to choose the discretization ahead of time is the key point. Yes, ultimately every continuous time or solver does discretize things, but the point is that it gets to control it and it gets to look like how complicated are the dynamics at this particular state and this particular time. And if things are really hairy, it can go really slow. And if things are really simple, it can take big steps. But if we choose ahead of time, we're probably not going to be able to trade those, speed versus precision off very well. I hope that answers the question. Okay. Yeah, so actually, I guess a good analogy would be like using fixed precision versus floating point numbers, right? We want to let everything be floating point so that our system can adapt to whatever the scale of what's going on. So, anyway, so how do we, so I'm going to say I love this model and I think it's like underused and it's like the future, but one problem is that it's sort of set up for discrete time settings still. So how can we make a continuous time version? So the simplest way is, oh, I can see the chat now. Great. I've never worked that out before. So the simplest thing, the first thing we tried is to say, okay, let's imagine that our system has some unknown state at time 0, and then we're going to say that its state evolves according to an ODE. We can learn that ODE, and we can learn the likelihoods, and then this will hopefully do everything we want. So here's the generative model, which is Z of T0 is like the state of our patient when they enter the hospital. And then F is the dynamics of like human physiology that says how their hidden state changes. X's are all the observations that we make about the patient. And we can do approximate inference to infer what the true state of the patient was when they entered, and then use the ODE solver to make predictions arbitrarily far forward or backwards in time based on that. And this is kind of nice. I'd say it's better than the RNN model in some ways because we have this well-defined state at all times, and we can learn the dynamics separate from inference. So later, if we have a new type of measurement, we can add it to the model without having to relearn the dynamics. For instance, that's one of the ways in which latent variable models are flexible in ways that RNNs aren't. Let's see. Oh yeah, okay. So here's a very toy example. So imagine that my data is one-dimensional, and it also is very sparsely gathered. So here's 3 different trajectories of maybe like, it's a toy data, but we can imagine it's like, patient's heart, ECG or something. So we can put our variational training objective into a stochastic gradient descent optimizer and jointly learn all the parameters at once. And that's what this looks like here. So we're learning the likelihood and we're learning the dynamics. And this is just a 2-dimensional slice of the latent dynamics, which in this setting are 4-dimensional. That's just a hyperparameter you could choose. Basically, the rule of thumb is make it bigger than you think it needs to be, and then it'll ignore the extra dimensions. Yeah, so we can learn the dynamics of the system and the noise on the observations all together at once. And so this is like a slice of that F function. Okay, any questions about what's going on here? I realize here I'm glossing over the whole machine learning machinery to actually fit this stuff, but it's something you can code up in like PyTorch or whatever you want. There's nothing fancy on the training side here. It's a standard variational objective. Okay, so this actually did work pretty well on the medical data. And so if you ever have a problem like this that you actually want to, oh, great. There's some questions. I'll come back to those right when I finish the slide. If you ever have a real problem like this, you should definitely start with a recurrent neural network where you feed it the difference in time from the last observation. So we call that RNN delta t, and it kind of does okay at like interpolation. And then, you know, these are different fancy versions with like different simple parametric forms in between observations, and then the fanciest and most general version does the best. Okay, and for extrapolation, the model that I'm saying is most appropriate, this latent ODE model, again does the best. But of course, it's not that informative. Like, you know, we kind of made this like fancier model and it works better, right? Okay, so a couple questions. How do you know you're learning the signal and not the noise? I mean, I will just say that the objective that we're training is the variational lower bound, which the larger it is, the smaller the distance from the true posterior. I mean, yeah, I guess I'd say that's a great question. We certainly could overfit because we're estimating the dynamics parameters by maximum likelihood. And then the sort of general claim is, well, as long as you have enough data, that you probably won't overfit. But it's certainly like a danger in practice. And it's one of these things where we have so many rules of thumb on how to deal with it. And it's sort of less of a problem than you might think, that I kind of maybe gloss over it a little bit. Anyway, how is the vector field parametrized? Oh, sorry. That's also a great question. I guess I would say it doesn't really matter, which is another way of saying like my students did it a long time ago and I forget. But, you know, in the demos that I coded up, this was just a fully connected neural network, like a multi-layer perceptron with maybe like a 10H hidden unit. There's one caveat: because these are ODEs, you can't use ReLUs, you can't use rectified linear units, because then the solution to the ODEs won't necessarily be unique. So we have this like one minor restriction. We have to use continuously differentiable nonlinearities, but that's fine. Like ALU is also fine. Like pretty much, there's lots of standard ones that fit fine into this ODE framework. Okay. Oh yeah, and so one nice thing about, well, there's one refinement that we tried that only helped a little bit, which is this latent ODE plus Poisson. And what I mean by that, is it a linear map from hidden states to observations? So in this toy example, yes, we just say that the, no. Yeah, so in general, I actually forget now if this is linear or nonlinear map, but it's a toy example, so either would work. But in general, this map will also be a neural network. How is the vector field initialized? I guess I'll say it doesn't really matter. Like it's just randomly doesn't. We're sort of in the land of where deep learning works, where things are over-parametrized, and like as long as you over-parametrize things enough, everything's going to work with enough sort of optimization. I realize that sounds very insouciant, and I guess I'll just say it's fine. Although, you know, the students do have to iterate on these things sometimes to get them to work, but it's usually just like fiddle around with the initialization, and we're not so afraid of local optimum as maybe we used to be. Just because things we sort of now think that the higher dimensions you're in, the less of a problem this is. But we can get back to that if you want. Okay, anyway, one cool thing that you can do with time series models is that you can condition on the fact that an observation was made. So sometimes the fact that somebody made an observation is already very informative about what's going on. So for instance, if I have two medical histories and I erase what all the actual numbers and measurements were, but just keep the timings, and one of them is like, you know, someone's getting a checkup every year, and the other one is this person gets a checkup every year, and then suddenly they're getting all these tests done. Probably the second person has something going on and they're less healthy. Jason Eisner at Johns Hopkins has actually worked a lot on this, these like Hawks models where they say, oh yeah, we can actually say that the use of Poisson process likelihood is like the only sensible likelihood in continuous time that says, well, let's imagine also learning a function lambda that is the rate of observations that we expect to see, or the probability of an instantaneous probability of an observation given the state of the patient. So this can just be another neural network that we learn and jointly do inference and learning with everyone else. And here's like a simple sanity check on that medical data, where here's somebody whose blood pressure was measured very often at the beginning of their stay, and the model was able to model that this was a likely time that he would have his blood pressure taken. Same with this like blood O2 stuff. So this is just a sanity check. It's a nice thing that you can do, and the reason people don't normally do it is because you need to solve an ODE or do a continuous time integral, which you can throw out to an ODE solver. And so it's like, well, we already have an ODE solver in our model, so why not just add this to the state and then we get a Poisson process likelihood for free. Oh, the vector field belongs to an infinite dimensional space. Well, sure, but any time we're learning, so the question is, you must choose a basis and truncate if you want to learn an infinite dimensional vector field. And I'll say yes, but that's true of any time we're estimating any function, is we have to choose a finite parametric approximation. Okay, maybe Bayesian non-parametrics could say something about that, but like, you know, we know that we know that it would take, you know, trillions of parameters to model anything perfectly, and we just get away with millions instead, and it's sort of okay. Yeah, we're definitely, you know, the more parameters we added to our model, the better job we could do in principle, and we just have to choose the cutoff somewhere. Okay, so I was saying this is my model that like does what I hoped, which is have continuous time dynamics and can handle observations at any time. However, it's really weird because it's deterministic. So it basically says, you know, you were born with some particular state, or you came into the hospital with some particular state, and then everything that happens since then is just the consequence of that one state. And you know, maybe this is true, like if we had like a clockwork universe, but even then, like then we'd have to have such a huge state. It becomes untenable. And if somebody like gets a disease or gets hit by a car when they're 20, somehow we have to like stick that again into their initial state, and it just doesn't really make sense. We think that there's all sorts of little unobserved interactions and things that are happening to the person that we have to somehow, you know, keep track of the fact that we're uncertain about those. Oh, do we quantify the uncertainty both within the inputs and the SDE? So for now, there's no SDEs yet, but for now we're going to have point estimates of the parameters of the dynamics and the likelihood, and then we'll be keeping track of our uncertainty about the states of the people or whatever the system is. Okay, so yeah, but we're gonna move to SDEs now. So I'm saying we should have stochastic transition dynamics in the sense, not that the dynamics are stochastic, but rather every time the state updates, some unknown perturbation happens. So going back to this model that I said I really liked, this deep Markov model, every time that they update the state, there's some randomness. One way to parametrize this looks kind of like this, where we say, okay, the new state is the old state plus some dynamics function that depends on the old state plus some noise, right? Like that's kind of, without loss of generality, we can frame things this way. And another nice thing about generative models is that they handle observations or missing observations like automatically. So if, for instance, I didn't observe data at one time point, and I wanted to ask like, well, how does that change my likelihood, like the marginal likelihood, marginalizing over all the z's? The answer is that it integrates to 1. So I can just leave off that term entirely, because I know that if I actually do integrate over all the z's, this thing will sum to 1. So it's just like the easiest thing you could ever ask for. If I don't see data, I just leave that part of my model out, and I still get the right answer. So I can imagine saying, well, what if I had a whole bunch of steps in between every observation? That would still be a valid instance of this model. So let's take the infinitesimal limit of, you know, smaller and smaller steps and more you know, fine-grained trajectories. And what do we get? Well, we get a stochastic differential equation. And I really mean the like standard SDEs that people have been talking about for 70 years. There have been a few machine learning papers where they say, oh, let's just add randomness to like an ODE solver and call it an SDE and stuff. And those really bug me, because there's already things called SDEs, and they have, you know, much better behaved asymptotics. So, okay, so to be specific, our old model was this ODE model that looks like this, and we want to somehow add noise to it. So we're just going to keep the deterministic part of our model, and this f, and add a new function, which is sigma, and it scales the noise. And this dBT, for those who aren't familiar with stochastic differential equations, that just means the change, like the difference between two times in a Brownian motion, which are marginally Gaussian. So this is just a roundabout way of parametrizing a independent Gaussian noise in such a way that we can take infinitesimal limits with respect to time in a sensible way. So for those of you who are familiar with like Gaussian processes, or other non-parametrics, this is actually like pretty similar in that we write down these two functions, f and sigma, and maybe define like a starting point. And we've implicitly defined an entire distribution over functions. It's kind of like when we define a kernel function for a GP, and then that defines a distribution over functions. Same sort of thing. Okay, any questions so far? Great. Okay, and so again, I really want to model, it's all on the surface of modeling. So what are SDEs good models of? So I'd say, I think the general consensus is they're a natural fit for many small unobserved interactions. And of course, the original SDE was, Brownian motion, where this guy Brown was looking at pollen that he knew was dead under a microscope and looking at it wiggle and trying to, and then Einstein's, of course, famous contribution early on was to say, oh yeah, that's because all these little individual water molecules are hitting it. So the similar sort of like many tiny interactions that you don't get to see happens like in a gene pool when every time animals die or have a baby, their allele frequencies go up and down a little bit, or prices in a market where every time people trade or learn things, the prices change. And one thing that like I think is not obvious when people who aren't familiar with SDEs is I'm saying, oh yeah, we have this Gaussian noise here. And they might say, well, weren't you just saying Kalman filters are lame because they're linear Gaussian? And here you have this like locally linear Gaussian thing. It's like, no. It's a good model. It's the infinitesimal limit of a whole class of interactions that just have to have something like finite or well-behaved variance. It's the central limit theorem is what's making this Gaussian. So the rest of this talk is basically going to be the standard deep learning approach of, okay, well, let's stick some neural networks in not just the drift function, but also the diffusion function and fit these to data. Okay. All right. So now I'm just going to tell you about the two technical problems of why people didn't do this until like a year ago. And you shouldn't take my word for it that these are like, it seems like they're just like simple things that should have been solved like 50 years ago, but they weren't. So anyway, so ultimately when we want to fit these models, we have some scalar loss function, all the parameters of all our neural networks, and we need to find what is the gradient of our scalar loss with respect to the parameters. We're going to send that to an optimizer, gradient-based optimizer, and fit everything. And so like the problem is, well, what if my model has some ODE solution inside of it that depends on theta? So you can just backpropagate directly through all the observations of whatever solver you use. The problem is that has a high memory cost. So the only scalable way to compute gradients when you have a scalar loss and millions of parameters is reverse mode automatic differentiation, which is the same as, well, it's a form of the adjoint sensitivities method. And that requires you, in most settings, to memorize all the intermediate states in your whole system that you're differentiating through, which just makes you run out of memory for like large systems that you're running for a long time. And also, it doesn't directly control the numerical error of the derivative. But anyway, so one very nice bit of math that was worked out, I guess, 70 years ago now by Pontryagin is to say that, okay, standard backpropagation involves a whole bunch of vectors times Jacobians, which can be computed cheaply without ever instantiating these Jacobians. And then you end up summing over all the layers in your neural network. For ODEs, or rather, you can take the continuous time limit of this, and you end up with an ODE that says how the gradient of the system evolves. And it, again, only requires computing Jacobians times vectors, which is cheap. And it requires solving an ODE, but like, by assumption, we already have an ODE solver. So if we want to compute all of our gradients here, we could just build this augmented system that involves vector Jacobian products and pass that to another ODE solver. So the general way this works is like, when I'm training, I see my data, I run some ODE or SDE solver to make a prediction, then I see how well it matches the data, then I need to run an ODE or SDE solver backwards to compute all the gradients. Okay, and the cool thing is that for continuous time systems, you can just run them backwards to reconstruct all the intermediate states, which is something you can't do in a general neural network. And all you have to do is stick some negative signs in front of F and T, and then send that to an ODE solver. So this is really great because it means that we have constant memory cost gradient computation, which is normally can be a limiting factor for training these large models. All right, any questions? Okay, cool. Yeah, so just so we're going to come back to this later, but here's the ODE adjoint sensitivity algorithm written as just like build this augmented system, send it to an ODE solver. And of course, yeah, this is all just old math. I did not invent any of this. So as an academic, I want to have my one trick that I apply to every problem and get new papers out of it. And an SDE I'm saying is like an ODE with noise, so why don't we just do the same thing? And again, like it blew my mind looking around the literature to realize that although there were things called like backwards SDEs, no one had actually worked out how to compute SDEs sort of backwards in time in the way that are necessary to do this trick. And in fact, some serious probabilists, so Sen and Maxime Rodzinski, who you guys probably know, actually wrote a whole paper about this and talking about how to construct these models, and then saying that we don't know how to do adjoint mode, reverse mode differentiation for SDEs in 2019. And that was like so delightful for me, because that was like when we were just starting to like have this thing worked out. Yeah. And I didn't think, you guys shouldn't take my word that this is hard. Take Maxime Rodzinski's word that it's hard. Okay, so for mathematicians, like this is the funny part, is like, okay, so the question is, just here, what we need to do is need to sample a strong solution to an SDE, or like a sample path for an SDE, and then integrate it forwards in time, and then somehow integrate some other system that will reconstruct it in a strong sense backwards in time. And so, okay, I learned, know about like Ito versus Sretanovich, and I realized like there's a little bit of subtlety here, but ultimately, if we're in the Sretanovich setting, surely we can just slap some more negative signs onto the new terms in our differential equation, and then like run the integral backwards. Like how can it not work if you write it out? It looks fine. And I talked to a probabilist at U of T, Leonard Wang, and he just kind of laughed at me, and he's like, what does that even mean? Like you have a forward filtration, and now you're going to, and that defines like this process, and then you're going to also like have a reverse filtration. Like it's like divide by zero. It doesn't make sense. And I was like, well, I think it's right, but I can't prove it. So him and Joy Chen, who's this amazing undergrad, spent like a month and showed that it's correct, and actually found that the Kunita, one of the original SDE guys, had sort of been writing in a sort of informal way about some of the similar ideas. Okay, so this amazing result that anyone else would probably think is trivial is that you can just slap negative signs onto the whole SDE in a Sretanovich setting to run it backwards and reconstruct the path in a strong sense. Any questions about that? Any SDE experts here? Okay. And then the other part of our contribution is algorithmic, which I think is nice for anyone dealing with like Gaussians or Gaussian processes, which is, okay, we need to somehow also store the noise that we use on the forward pass so we can run it backwards on the reverse pass. But this requires sampling an entire function, which is hard. And we don't want to memorize all the points that we sampled on the forward pass, because then we'll, again, be using more and more memory. So there's this thing called a Brownian tree that had already been used for some adaptive SDE solvers, which basically says, okay, I can turn my Brownian motion into a Brownian bridge by just sampling the first and last points. Then everything is marginally Gaussian in between. I can now, if I want to evaluate a sample at a particular time point, I can just evaluate at different time points on this SDE, bisecting the time intervals until I get to the time that I want, or like, close enough. And I'm zooming in, exponentially fast. So this is like so if I'm careful with the random seeds and I make sure that the random seed I'm using depends on the branch of the tree that I'm in, I can like forget about all these samples and then go and resample at any point here with only storing the seed at the very seed, the seed at the very top of the tree. So this is a new algorithm. It's like just a slight extension of the old one due to like Terry Lyons, that shows how to sample any point on a Brownian motion in constant memory cost. Oh, question, can you talk a bit more about the filtration? Are we simply treating the end state as the initial condition? Yeah, so we basically end up, I would say, I don't think I could summarize it in a more helpful way than I did right now. Maybe we'll come back to that again. Yeah, we end up just defining a different process that runs backwards in time. Okay, so the punchline is, here's the adjoint sensitivity method, like 70 years old. And now 2019, here is the generalization to SDEs. And so now we just have this new diffusion function and a Wiener process sample. We augment the diffusion process backwards in time. And it's like very nice and simple. So now we can compute gradients through SDEs. Oh. Internet for a second there. Am I back now? Okay, anyway, yeah, so now we can compute SDEs gradients through SDEs in a scalable way and fit however many parameters we want for the same time cost as just running the SDE forward in time, like almost. Yeah, basically, people have been like fitting small SDE models. Like Chris Rukakis is always saying, oh yeah, use Julia and you'll fit your SDEs really well. And it's fine, the approach that he advocates for small systems where you can actually store the state. Either by doing forward mode integration, which is slow, or backward through the solver, which is high memory cost. So we have almost the best of both worlds, constant memory and L log L time. But that's actually sort of better than it looks most of the time. Anyway, so new algorithm. Now let's fit some large SDE models. Okay, and there's one last detail before we can fit models, which is what's our training objective be? And it shouldn't be to just match the data, because then we would never learn the stochastic part. We would always say, oh, I can predict this trajectory arbitrarily well by just learning some complicated dynamics that happen to reproduce the data everywhere. So again, we're going to want to fit this into a variational autoencoder framework where we say, okay, we'll have one SDE that says what is the, we have initial state, and then we have our Brownian motion that then says how does our state evolve. So all the randomness ends up in this like infinite dimensional random variable, this W. And then instead of an ODE solver, we have an SDE solver. And then again, we can generate our data. So this is the same again as before. We have a latent variable model, but it's an infinite dimensional latent variable model now. And then to speed up inference, we'll have train a recognition network that looks at the data and outputs the parameters of another SDE that'll tell us what our approximate posterior is. Okay, so that last part is like a little bit hard to digest. So yeah, sorry. So again, this is the generative model. Same as before, we just have latent state observations. Now, once we've seen data though, we have, like that defines a prior on functions. Now we need to define a posterior. We can just use another SDE to define the approximate posterior. So this took me a long time to digest, and I hope I'm not going too fast. But the idea is that, well, actually, I'll just show you an example and it should make more sense. Anyway, the point is that the variational lower bound can still be expressed as another SDE that basically looks at what is the difference between the drift of the prior and the approximate posterior. And we just integrate that through time. So the standard training objective, it can be expressed in continuous time settings as well. And that was mostly worked out by other people before us. Okay. So fitting this model, what does it look like? So here is a setting where we have some data. These are the black crosses our data. We have a prior SDE. So just like in GPs, we have a prior before we've seen the data, and we're gonna have a posterior after we see the data. Here we'll use an Ornstein-Uhlenbeck prior just because it's easy to code up. And here the blue shaded area shows us the density, the prior density of our process before we've seen data. So it's an OU prior. And these purple jagged lines are samples from this prior. These are example trajectories we might expect to see before we've seen any data. Okay. Now we're going to optimize the parameters of our approximate posterior SDE to maximize this variational objective that tries to make our approximate posterior close to the true posterior. Okay, here's what that looks like. So there's a few things going on here. So these gray lines here are showing you the drift function in the approximate posterior SDE. So basically what has to happen for the approximate posterior to be a good, close to the true posterior is that we have to sort of steer the trajectories towards the data. I mean, of course, like in general, it could be some crazy complicated thing. For the most part, if we have a likelihood that's like unimodal, so here we have the Plas likelihood, then I think the true posterior does look something like this. Of course, we can never see true posteriors exactly. And yeah, as it sort of makes sense. So if I imagine we can follow this trajectory sampled from our approximate posterior, and it starts down here, but then the drift pushes it, in general into this direction, and then down, and it follows the data roughly. So what inference looks like in this model is learning the diffusion function, or sorry, the drift function that makes the trajectories match the true posterior. And the cool thing is that, like in Gaussian processes, as soon as we have complicated likelihoods, the true posterior is no longer a Gaussian process. But here, even if we have a complicated likelihood, we haven't worked this out formally, but we're pretty sure it's true that the true posterior can also be described arbitrarily well by another SDE of the same form. So basically, our family of approximate posteriors contains the true posterior if we make the neural networks large enough. Anyway, if any mathematicians want to help me nail that down, I'd be happy to chat. What does it mean to have an OU prior if f theta is a neural network? Oh, well, I mean, f theta is the prior, but like a zero function. So an OU prior has zero drift and -1 diffusion function. And we could just say, oh, the prior is a neural network that's just the zero function, right? That's just a special case. We could also learn the prior if we want. Like that's where we would learn like if we weren't wanting to learn human physiology across a whole bunch of patients or learn the laws of physics, that would end up showing up in that prior. Because that's the prior before you've seen data for this particular patient or something like that. Okay, we'd be able to come back to that. Okay, so I'm saying now this latent SDE model, like, people have like thought about this model class before, but I'm saying now we have the tools to explore it, and it is pretty unexplored. As I've been saying before, we can stick any differentiable likelihoods in here, use adaptive SDE solvers, and it should scale to millions of parameters and huge states. And we can use adaptive Milstein solvers, for instance. It's like one detail that we weren't sure, but it turns out that you can use that for the forward and the back pass. So this isn't million parameters, this is 11,000 parameters, but here's us fitting our latent SDE model to motion capture data, which is like 50-dimensional alterations per like frame. We chose a 6-dimensional latent space, but that's just, we're not sure that's a particularly good number. And 11,000 parameters is like nothing by neural network standards, but it's giant by SDE standards. And there's no reason why we couldn't scale that up anymore. Everything scales, I think, like roughly linearly in the number of parameters. Of course, when we first coded this up, it was all in PyTorch, and it like didn't quite. There's all this Brownian motion stuff that we hadn't yet worked out how to put on the GPU. But now, so it was a bit slow at the time. I think now it'd be fine to scale this up to like 1 million parameters, and it worked better than the deterministic methods, right? Like, of course, it generalizes them, so it has to do a little bit better at least, right? Okay, so that's it. So we have this new model class that now we know how to fit. We're just starting to play around with it. It should be able to handle real irregularly sampled time series just fine, and I'm hoping to start some collaborations. And it also can condition on the time observations. Everything sort of, it's a deluxe version, right? You can answer any query we want. We can, if we wanted to know like which time do I need to observe something in order to reduce my uncertainty about some other prediction, that's something that you can totally, compute easily with gradient-based, optimization. Again, this is all getting a little complicated. We have a nice package, open source package, but you should always start with a recurrent neural network. Like that's always going to be the simplest and fastest thing, and it just probably won't work as well. So the next steps, in fact, talking to a math audience, I think there's a lot of open problems related here. So one is, how do we generalize this to things like jump processes or Levy processes or stochastic PDEs? Because there's other types of stochasticity that we haven't really talked about. And I think some of the math for that is done and some of it isn't. But also, like, how do we generalize that virtual Brownian tree, for instance, to sampling from a Poisson process or something like that? I think that would be like a fun mathy project. I've also been playing around with applying this to make infinitely deep Bayesian neural networks. But I really want to start some collaborations in like population genetics or epidemiology or finance or whatever. So, if you have some data that you want to try this out on, let's talk. Last thing I wanted to add is I've just been playing around with the idea that we probably want to have multi-scale models because we often think that there's like some slow-moving thing, like the size of a person that changes. It's very easy to predict and changes very smoothly over time. That then determines the fine-grained details of like, how fast their heart beats or something. And we can massively speed up training these models by skipping over the fine details in between observations. So I think we can do that. And I think there's like a straightforward mapping from any sort of hidden markup model to a set of differential equations that have like, some particular dependence of the variables. So that's sort of like what I'm excited about right now is to say, well, we don't necessarily, we know that reality has like Planck scale dynamics and we don't really want to deal with those directly, but maybe we can put those in the prior and have the approximate posterior have this nice multi-scale structure that we kind of do when we do physics and we talk about like temperature and pressure and these other sort of made up variables that we think help us predict and explain these truly fine scale systems. Okay, very last slide. So this SDE stuff isn't a great fit for modern deep learning packages because it involves a mix of like control flow and random number generation and neural networks. So normally deep learning, like GPUs want you to have a big chunk of computation that you're going to do the same thing over and over again every time. But I want to use adaptive solvers, which then have like control flow and all sorts of like little fiddly things. So I've been playing around with this very experimental programming language called DEX. And for those of you who are like programming language aficionados, think like Julia, but designed by people who actually know about programming languages and made a good type system. So it's dependently typed, which is also fun and sexy and exciting, and strongly typed. And it means that a lot of the like numerical issues, we should be able to handle them in much more principled and general ways. And we do compile time debugging and not just write a million unit tests. So this is it's very bleeding edge. I think I'm the only user in the entire world right now, but I invite you to go check it out as well. Okay, so I want to say, the bulk of this work was actually done by Zhouchen Li, who's this amazing student who was an undergrad when he did this. He's heading to Stanford now. And then Leonard Wang was the probabilist who helped us work out the reverse time SDE details. And then Ricky Chen and Yulia Rubenova also basically did all the ODE stuff. So with that said, thank you very much for having me. Any questions?
Yeah, thank you very much for your talk. We have time for a couple of questions. I'm gonna start with one question. It's not particularly towards like the SDD part, but like the neural ODE part, because you have backpropagation and then the continuous time equivalent is like the the adjoint sensitivity method. So when you look at like those discrete time models, like those recurrent neural networks, you have the problem of like exploding and vanishing gradients when you train them with backprop. Does the smoothness of the adjoint sensitivity method help? Or do you also have to choose like topologies where like the errors flow nicely?
Yeah, that's a great question. So I guess there's two parts to the answer. One is that it's not as bad as you think because, let's see, here we go. So the old kind of recurrent neural networks that really had a hard time with this would just say that z of t plus 1 is f of z of t. And residual networks, which is like this massive innovation, just said, no, let's do z of t plus 1 is z of t plus f of z of t. And that already kind of fixed most of the problem and let us train very deep neural networks. And it's kind of like, I think, an embarrassingly simple trick. I mean, LSTMs also had it was sort of a more complicated version of this trick that addressed the same problem. And then I guess I'll say there have been a couple of papers bringing some more of the tricks from LSTMs to ODE architectures, specifically gating, to say, oh, sometimes we want to be able to turn off, the influence from some particular dimension with another part of the neural network. And that does seem to help make them more stable. We didn't put any of those tricks into any of our models that we trained here, but maybe we should have. I will say though that we did have one trick actually when we trained the train this SDE that's related here. I said we have an OU prior, and that OU prior is doing something kind of like what you're saying, which is that it's always pushing the trajectories back towards 0, which is nice for stability. So we parameterize the approximate posterior to be the OU prior plus something that we learn. And so the point is that we start off with something that's very stable, and then we sort of, if we want to go off to infinity, we have to learn, sort of push against the prior, rather than just by doing it by default.
There's another question. It seems like the most recent setups of fully continuous time RNNs are a subclass of your latent ODE framework. Have you connected or compared these?
So I guess I'm not sure exactly which fully continuous time RNNs that they're talking about. I mean, the thing about, so sometimes people say neural ODEs are a continuous time RNN, but I think that's a little funny because RNNs usually update at every step. So even this weird lingo looks better than Julia. DT. Oh, sure. So if you're just saying that like the change in dynamics is given by a neural network, I mean, yeah, that's a neural ODE. It sounds like it's the same model class. I guess, do you want me to read the next one?
Yeah, sure.
Do you think you could extend this approach to solve an inverse problem? Let's say you know the dynamics and have some measurements and want to know where the states of the system are in some places you didn't measure. Yes. So I've been saying so far, let's just learn everything from scratch. But I guess I didn't put them together. But the point is, this whole system setup totally works if you know the dynamics. Like if you know this F and this sigma ahead of time, that just makes your problem easier. And then the learning, again, is just going to be about solving this inverse problem. Like this, that's what's happening here, is that I have my prior and I have my data, and I'm just trying to, estimate the hidden states or get an approximate posterior over the hidden states. So it's exactly appropriate for these inverse problems, yes.
Do we have more questions?
Have you used this framework to learn residuals of some known physics? So no, but that's because we haven't used it very much because it was slow, and then Chen went to Stanford. But like, I totally think we should. And I mean, so yeah, Chris Rukakis is always saying, let's take the physics model that we know is like approximately the right thing, and then add a residual neural network and just learn the residual part. And like, if you know some part of your system's dynamics, absolutely stick them in there, right? And that's one of the beautiful parts about neural networks, is it's just saying, oh, add some extra big parametric part to capture all the stuff that you don't know. So can we view these slides elsewhere? Yeah, I mean, these slides are on my website, and I'm sure that I'll send them to the organizer afterwards to be uploaded to some relevant site here. So, yeah, if you just go to my main page, and then this paper is there, and then it has slides. So.
Okay, if we don't have, I technically have like one last question. So when you have like a hidden Markov model, you always, or like you always need to solve this like nasty integral over the previous state.
Mm-hmm.
And that's basically the bottleneck for these. Like, does that problem come up here as well?
Yes, it does. So that's kind of what I was trying to talk about here. So here's where you actually solve an integral over all the states. But you're right, it can be broken down into like a dynamic programming problem where you solve one of these states at a time. And if you do this in discrete settings, it has a cubic, or like, well, I think quadratic time cost in the size of the hidden state. So that's what the recognition model is for, which is something that I kind of glossed over. Sorry, let me just go back there. I should just, okay. So one way to estimate that integral is by Monte Carlo and importance sampling, and say, okay, well, if I have a distribution that I can sample from that I think is close to the true posterior, and I sample from it, I can estimate that integral. That's essentially what variational inference is doing, and variational autoencoders is they're saying, well, hopefully this recognition network will output a distribution over the states that is close to the true posterior. And then I can, and then I'll just get a Monte Carlo estimate of that integral. So I use that Monte Carlo estimate to help me learn the parameters of the prior, and simultaneously, I also can estimate how good that approximation was. So that will let me learn the parameters of this recognition model all together at once.
Thanks. Okay, let's take a last question, and then I think, so
Oh yeah.
it's in the chat.
Sure, so the gradient is computed with respect to a single realization of the Brownian motion, which has measure 0. How is this relevant to capturing the bulk of the trajectory? Yes, so as I was saying, we're using Monte Carlo to estimate these integrals. We're also taking a different realization of the Brownian motion every single time, every iteration of our stochastic optimization. So that's kind of the beauty of stochastic gradient descent, is that if you have some other things that you can estimate by Monte Carlo, you can just throw them in there, and now you're going to sample the data point and the any randomness in your model, and then any randomness from your Monte Carlo approximations. It all just goes into this giant soup of variance that, like, hopefully isn't too bad. So yeah, we're integrating over the Brownian motion by just changing it every single iteration.
Okay, yeah, thanks a lot for the great talk. Usually our talks are bi-weekly, but we're gonna skip next week, like in 2 weeks, because of Thanksgiving. So I hope to see everyone again on December 13th for Cecilia Clementi's talk. And yeah, thanks a lot for your talk.
My pleasure. Thank you. Thank you for having me.
Bye-bye. Thanks a lot.
Bye.